Hello everyone, I'm Ze Yusen from Peking University. This is our paper, Improving Machine Translation Systems via Isotopic Replacement. I will first introduce the introduction of our paper. Machine translation is able to translate between thousands of pairs of languages effectively in real time. The tools such as Google Translate and Bing Translator are widely used in people's daily life. Nevertheless, such machine translation systems are not perfect, and the bugs that users experience have a different character from those on traditional non-machine learning-based software systems. The consequences of machine translation have long been studied, and their effects have shown to be serious. For example, mistranslations of the Article 17 of the Treaty of Retraining lead to a war. As we move to a scenario in which machines routinely translate natural language sentences, the potential for misunderstanding may be magnified. This makes automated translation an important new application for testing and evaluation. Recently, quite a few approaches have been proposed for testing machine translation systems. To test this system, a promising trend among those approaches is to use word replacement. For example, giving the sentence, "Women do good research in computer science," a testing approach, TransRepair, can generate an input sentence by replacing the word woman with a similar word, man. This input sentence is further paired with the original sentence as the test input. Then, the testing approach feeds those two sentences to the machine translation system. Since there's only one word exchanged in those sentences, their translations ought to be similar to each other. In this example, there should be a one-word differences between those two translations. However, if the translations are not similar to each other, the testing approach reports it as an inconsistency bug. Those approaches are good. However, precise control of the impact of word replacement in those word replacement-based approaches is still difficult due to the fuzzy semantics of the natural language words. For example, the word great in this sentence is not suitable to be replaced by the word good. To tackle this difficulty, we propose a novel word replacement-based approach called CAT to machine translation testing. Given a sentence in the source language, CAT performs isotopic replacement to generate new sentences. And the goal of the isotopic replacement is to control the impact of word replacement. Those are the examples that isotopic replacement should avoid. For the left example, context is not considered, where the numeral 6 is not suitable in this context. While for the right, the semantics of those two sentences is not preserved, where a great shame is different from a good shame. To realize this isotopic replacement, we first conduct context-aware word replacement, which replaces a word within a sentence with another word that is also suitable for the context. Then, we calculate the context-aware semantic similarity between the original word and the replaced word, and use this similarity to discard the word replacement that influences the semantics. Following a testing and repair approach TransRepair, CAT can test and further repair the inconsistency bugs. Then I will introduce our approach. Giving an input sentence and a word within the sentence, CAT aims to identify a set of words, each of which can be used to replace the word. To realize it, CAT contains two states, candidate word generation and semantic evaluation. Candidate word generation generates a set of candidate words for each word in the input original sentence. During generation, we should ensure that each candidate word is suitable for the context. Thus, we use BERT to encode the sentence context and further check which words are suitable for the context. In detail, given an input in the past decades, we first replace each word with a special token, mask, in turn, and feed the masked sentence to the BERT model. The BERT model can predict a set of candidate words that are suitable for the context. Those words can be used to fill the mask and generate a new sentence. After we got those candidate words, we found that they are sometimes only suitable for the context, but have different meanings from the original word. To realize isotopic replacement, we still need a semantic evaluation to discard those inappropriate words. Thus, we propose a novel neural-based mechanism to compute the context-aware semantic similarity and use this similarity to discard the inappropriate words. In detail, we measure the context-aware semantic similarity between the original word and its replaced word by BERT. For an original sentence and a set of sentences generated in candidate word generation, we feed them to BERT, and BERT outputs a vector for each word. We select the vector of the original word, for example, in, and the vector of the replaced word, for example, within. Then, we compute the cosine similarity between those two words as the context-aware semantic similarity. If the similarity is larger than our predefined threshold, we add the generated sentence to the final set for further testing and repair. The process of testing and repair in CAT is the same as TransRepair. Thus, we only have a brief introduce here. For testing, given an input sentence, we use the above sentence generation approach to generate a set of mutants. Each mutant is paired with the original sentence as test input. Then we feed each test input to the machine translation system and compute a metric between their translations. If the metric is below a threshold, we report it as an inconsistency bug. For repair, giving an test input of an inconsistency bug, we repair the translation of each sentence in the test input in turn. For each sentence, we first generate a set of mutants via the above-mentioned sentence generation approach. Then, we feed them to the machine translation system and ranking all translations by a ranking metric. Finally, we select the best translation, namely the translation with the highest ranking, and maps it back to the original translation as the final repaired translation. This is an overview of CAT. Then, I will introduce the experiment. In this paper, we focus on 4 research questions on the effectiveness of test input generation, bug detection, and bug repair, and the efficiency. We conducted experiments on 2 machine translators, Transformer and Google Translate. The dataset we use is the news commentary dataset. Since CAT follows TransRepair, we select TransRepair as the baseline. To answer RQ1, the effectiveness of test generation. For each test sentence in our dataset, we generate mutants with CAT and TransRepair, respectively. Each mutant is paired with the original sentence to form a test input. We then record the quantity, distribution, validity, and the diversity. For quantity, we found CAT generates nearly 10,000 test inputs, while TransRepair generates nearly 5,000 test inputs. For distribution, CAT generates 5 test inputs, which is the upper bound for almost all input sentences, while TransRepair fails to generate any test input for 43% of sentences. For diversity, we compare CAT and TransRepair from the aspect of the part of speech of the replaced word. We observe that CAT can generate mutants for 7 more types of part of speech. For validity, we conducted human evaluation. The experimental results show that 96.5% of the test input generated by CAT are valid. To answer RQ2, the effectiveness of bug detection, we feed the generated test input in RQ1 into Google Translate and Transformer for testing. As a result, CAT detects 129% more bugs than TransRepair on both 2 machine translation systems. For diversity, CAT can detect 7 more types of bugs than TransRepair. The validity of the bugs reported by CAT and TransRepair are similar. To answer RQ3, the effectiveness of bug repair, we net cat and TransRepair fix the same set of detected bugs. For quantity, cat repairs twice more bugs than TransRepair. For diversity, cat repairs approximately half of the bugs under each bug type, whereas TransRepair achieves competitive performance on only numerous, failing to repair 89% of bugs under other types. The validity of the bugs repaired by cat and TransRepair are similar. To answer RQ4, the efficiency, we record the time cost of cat and TransRepair during the process of mutation generation, bug detection, and bug repair. Cat is significantly more efficient than TransRepair in mutant generation and bug detection, and has comparable efficiency with TransRepair in bug repair. The last part is the extended analysis. We compare cat with other translation testing approaches in detecting inconsistency bugs. We observe that cat achieves better results than other approaches. This is not surprising, considering that those approaches aim to detect different types of bugs. Those are examples fixed by cat. To conclude, we propose cat, an isotopic replacement-based approach to improving machine translation. And the experimental results on Google Translate and Transformer show that cat performs better than TransRepair. That's all. Thanks for listening.